Okay. So we're going to start with chapter 20, right? So we'll start with our atmospheric chemistry, and we'll kind of begin with that, and then we'll move kind of on to our other ones. And so as we go through, if you have specific questions from that chapter that you want to work through, we can talk about then. And if it gets a little bit more detailed, then I might have you come back during office hours if it gets really specific. And so for this one, what we're looking for is we're trying to find the partial pressure of water, or sorry, we're trying to find the concentration in ppm. And so ppm seems to be a challenge in general, it's probably the most complicated of the concentration units from what I've seen. And so people seem to have been struggling with this one. And so I wanted to take a moment for you guys to work on this so that way you can kind of review what ppm means and how that might be related to our partial pressures. So there should be something that always pops to your head when they talk about partial pressure. Now, partial pressure really comes from Dalton's law, where your total pressure is equal to the sum of its parts. We also know that the total moles are going to be equal to their parts as well. And so we should understand that there's a connection between our moles and our pressure. So if we know that the partial pressure of water is 0.80 torr, and we know the total air is 735 torr, this is going to be related to the amount of material of our water over our air, which is kind of the same thing as us saying our water, and our air would be our solution. So if we want to turn this into a ppm, what do we need to do once we find this ratio of our water to our solution? What do you guys think?
We have to figure out the volume of water vapor in the sample layer.
Why would we need the volume of the water vapor?
So that you can figure out the parts per million.
Right. So this parts per million have to deal with a volume.
It's
mass.
It's molecules.
So it can be any of those. It doesn't actually have to be only volume. It doesn't have to be only mass. It can be moles, it can be molecules, it can be pressures, right? It can be anything as long as it's one part of it versus a million total. So as long as your units are the same, it doesn't matter what they are. So in a way, you could say that if we had 1 ppm of water vapor, that would be 1 torr of water to 1 million torr of air. We could have also said that 1 gram of water and 1 million grams of air is also going to be our ppm as well. So in that case, you don't want to have to be, as long as we can kind of get our moles to moles or grams to grams and things like that, as long as we can get them into the same unit, we can get that comparison there of how many parts to how many parts. So in a way, sorry, now I erased it somehow. There we go. We have a ratio here of our torr. We have this as 0.001088 for the amount of water to our air. So if we want, what we can do is this is how much water we have to 1 air, or 1 torr of air. And so if we want to change it to ppm, we just need to multiply this by 1,000,000. And we'll get 1,088 torr of water to 1,000,000 torr air, which is us being the same as our ppm.
So that's the same as multiplying 0.80 torr over 735 torr times 1,000,000 torr over 1 torr.
Sorry, you wanted to do
So like keep
0.8.
it at 0.80 torr of water over 735 torr of air times 1,000,000 torr of air over 1 torr of water. So the units would cancel.
Yeah, because this would still give us our ppm. The only thing is, yeah, that would all work out because these would end up multiplying, that would end up dividing. Yep, that is fine. So ppm does seem to be the struggle that people kind of have. It is commonly used when we make very dilute solutions. Instead of having to say that you had something like this or even smaller, people like to move into ppms. We especially see this in the health field where instead of talking about micrograms per milliliter, right, they can get things into a more similar type of range, or sometimes it's even micrograms per liter, right? And so ppm is something that you want to feel comfortable with as you're going through that. Sometimes atmospheric chemistry, the tricky part about it is you start to deal with larger numbers or smaller numbers than you're used to. And so you just want to kind of keep that in mind as you're moving forward. This one's a very typical one for our atmospheric chemistry. It's about us finding the energy of that photon. So I'm going to go ahead and break you guys into groups so you guys can work on that part as well. And let's go ahead and let's find that wavelength. I've gone ahead and given you the average bond enthalpy for our oxygen molecule, so you guys can use that as well. I'm going to split you into 3 groups so that way you guys can kind of get some practice. Okay? Do you guys have any questions about that part? So in a lot of ways, this one is very similar to like a normal stoichiometry problem. We just had to use pH, and then we have to use a very large number, right? And so a lot of chapter 20 is about that, just practicing those Chem 120 type of processes, making sure that you really understand them so that way you can apply them to larger situations. Because the answers you get are not quite as intuitive as they used to be, right? If we were doing this in a benchtop scale, it's a little bit easier to tell how many grams you need to add in. Does anyone have any questions on this before we move on into chapter 23? If you look at the end of chapter 20, there's some good kind of like practice problems. So if you've been struggling with chapter 20 in particular, because I know it covers like a lot of different topics, questions 0.67 to 89, so those ones at the very end of the chapter, they have some good ones in there where you're kind of combining these different topics inside. So if you're looking for some more additional practice problems, that's what I would recommend. Okay. Other than that, where you have complexes will be on this exam. And so we want to make sure we can do both. We should be able to go from a formula to a name, but also from a name back to the formula. just like your quiz, I will be providing you with the ligands names, right? So just in the same way that we had it on the quiz, there will be a text question where we'll have like the ligands with their different names with them, the same with some of the metals. And so you just want to make sure that you know how to apply those. So you don't have to have all of those memorized, but being familiar with them is something that's important. You do want to know which ones are bi, which means that they can bind with 2 sites, which ones are mono, where they only bind with 1. And then does anyone know how many sites EDTA binds to?
2. Or 4.
EDTA is our one exception. It's our big one. So it binds to more than 2. Does anyone remember how many?
4.
EDTA does a whopping of 6 of them. Right? So EDTA by itself takes into an octahedral. So you do want to make sure that you know that one because it does throw things off with
What's
your coordination numbers.
Yeah. Oh, that's EN. That's 2.
EN is 2.
Okay.
And then EDTA is the one that is 6.
Oh.
Right? So it's our big one. And that one, the only reason why I would like you to memorize that it does 6 is it's a very, very common chelating agent. And so there's a lot of titrations that you do where you will use it with the EDTA. And so it's just an important part to know. So on to that. Right now we have this metal complex. So I want to go ahead and get that formula from you. And so when we go through there, we can go ahead and start to break it apart. So this one is telling us that we have a ligand aqua, we have a bromo, we have a chloro, and then we have our metal down here at the end. So which one of them are we going to write first in the side of our formula?
Is it the metal?
What's going to be our first, what part should we translate first for our formula?
Dibromo.
Right. So the bromo doesn't get written first, right? We're not going to start it off with our BR. Right?
Oh, yes.
What do we always write first for our formulas?
Is it the iron? The ferrous?
It has to be the iron, right? We start with the metal. So we should start with our iron first. Then we should have, it doesn't matter. We could have it with our neutral ones or our bromo and our chloro. Normally, I just list them in the same way that they have up here. So aqua becomes what?
Water.
Water. And how many of them?
3.
3. Bromo is how many bromines should we have, or bromides?
2.
2. And how many chlorines?
1.
1. Right. Now, are all of these part of the same complex, or should some of these be like partner ions?
Is the chlorine a partner? Is it like outside of the complex, or is it inside?
So we have to look at the name, right? So if it's all written together, they are all part of the complex. If that chlorine wasn't part of the complex, we wouldn't have written it inside. We would have written it afterwards as chloride. In the same way that if we have partnered this with like a different metal, we would have potassium. Okay. So that's an important part to remember when you're translating them over, is that's how you can tell whether or not they're going to be part of your complex. If it's a metal and it's in the front, it's not part of the complex because all of our metals should come here right at the very end. If it's a ion and it's not part of the complex, it's going to come here after the metal, and it's going to be in this section, our anion zone, our anion zone. And it's going to end with like our ide or our 8 or whatever it normally would end in to show that's an ion. Right? So this is what we have right now. And because it's all a complex, we can bracket it. And so what are we missing so far? There's one last part that we should have on this. What was that?
The Roman numeral or the charge?
The charge, right? Roman numerals are only in the name, but we do need to think about the charge. So our iron is a 2+.
So -1.
And for these 3 ligands, is water charged or is it neutral?
Neutral.
right? Water is neutral, so we don't have to worry about that. Does bromine or bromide have a charge?
Yeah.
Yeah, so there's two of those at -1. And does a chlorine have a charge, or a chloride?
-1 as well.
-1 as well. So overall, what should the charge of our mellow complex be?
-1.
-1. A good way to check on that is we have this ending in an 8. And so if it ends in an 8, what does that tell us about the charge of that complex?
Anion.
It means that it's an anion, so it's going to be a negative charge. So you just want to make sure that you have those different parts as you're practicing through on those. Does anyone have any questions on that part? Do you guys want to see another one, or are we feeling pretty comfortable?
Yeah, could we see one more?
Yeah.
Okay.
Thank you.
Let me- All right. So that should be tetraamine diiodo cobalt 3. I guess I'm missing an I there. Chloride. So which one should we start with first for our formula?
Cobalt.
Cobalt. So start with our cobalt. From there, we can go ahead and we can either do the iodo or the amine. I normally do my amine first. And so how many of the amines should we have?
4.
4. And how many of the iodides?
2.
2. And then do we need to put the chlorine in right now, or do we do the chlorine later?
Later.
Later. So what should we do now in order to finalize our metal complex?
Find the charge.
Do we just put the positive like that?
The brackets.
We got to bracket it, and then we need to put the positive charge. Very good. And so now, how do I add in that chlorine?
Put it just outside of the bracket.
Just outside. And how many of them do we need?
1.
1. So now once I have that chloride in there, I don't need that charge anymore because now we're all balanced. In the same way with ionic complexes, you don't write magnesium 2 plus chlorine 2. We can remove that charge and we can put our magnesium right next to our chlorine. You can do that for your metal complexes as well. Does anyone have any questions on that part? I'm going to give you one formula and I want you to go ahead and change that back to its name. So kind of going in the opposite direction. I'm trying to think of a different one that I haven't given you guys before. So let's go ahead and change that to its name. When you have your answer, go ahead and put that up in the chat. I'd like to see you guys type it all out. I want to see kind of how we did. Right is close though.
Is that just an O?
That is just an O.
Is that oxo?
That is oxo,
Is it my charge on the ruthenium?
perhaps. The second one is in. Also not quite there yet. We're getting close, but we're still not quite there.
O has a +1 charge, right?
So O is oxide. What kind of charge would oxide?
-1.
So oxygen
Yeah.
is going to be a -2,
-2.
right? The halogens are all -1. The oxide has to be -2. Our charge is
rubidium
increasing.
or ruthenium?
But what was that?
Is it rubidium or ruthenium?
So Ru is going to be our ruthenium.
So it has to be +4. It has to be a charge of +4.
We need a +4, right? So when we look at this one, you guys started off correct in that it's going to be our pentaamine, sorry, our penta-aqua. And then we have oxo. You can put mono-oxo or you could just put oxo because it's all by itself, either one. Then we have our ruthenium. And now we need to figure out our charge. So if we look at this part, what charge does our complex have to have if we're balancing it out with 2 chlorides? Right? If we're balancing it with 2 chlorides, then this needs to be a 2+. And oxygen is another -2. So we kind of have a ruthenium that's trying to balance out -2 from the chlorides and -2 from the oxygen. So our ruthenium needs to be a +4. We don't have to change the ending because it's still a positively charged ion. Right? And then we need to say that we have the chloride. Now, do we need to put dichloride?
Yeah.
No.
We don't. We shouldn't have the dichloride because this is an ionic compound. If I were to give you just this part, this penta-aqua oxoruthenium 4, we should be able to have figured out that that would give us this ion here with our 2+. And then if I told you you were going to partner that with chlorine, then you would know that you would need 2 chlorines in order to balance out that charge. So in the same way that with your ionic compounds, you don't mix it with your mono, di, and tri, the same part for our supporting ions. We don't need to put in mono, di, or tri. We should just have the ion. So you guys want to make sure you practice these a little bit. On the worksheets, we did a total, I think, of almost 30 of them. And so that's still something that you want to work your way through. Your book has some more practice ones at the end of the chapter. They go through, let me see if there's the list of them. They go through from question 11 to about question 26, they kind of mix them in there with the naming and the structures. Does anyone have any questions on that part? Okay. This is the other part about crystal field splitting that we want to make sure that we understand, and it's about high spin versus low spin, and how that relates to strong field ligands versus weak field ligands. So I've given you an example here. Now, if we wanted to name this, this would be our tetra aqua dicyano chromium 2. And I know that it has to be chromium 2 because our charges have to balance. So we have our ligand there, our metal complex. And so we want to know how many unpaired electrons is that chromium going to have. So where do we start for a question like this?
By answering that CN is a strong field ligand.
Well, we know that CN is a strong field ligand because it tells us that.
Oh, it's I was asking if it was.
Yeah. So it tells us that it's a strong field one. And so from there, what do we need to look at in order to deal with paired versus unpaired?
How many valence electrons are in the D shell for chromium 2+?
Very good. We have to look at our chromium 2+. So we know that it has an oxidation number of 2. Sorry, an oxidation state of +2, because this is -1 and there's 2 of them. And so we can find that our chromium 2+ has how many electrons in its valence? Or sorry, not in its valence. How many D electrons does it have?
4.
4. Now the second part is we want to figure out what shape this is going to be, because that will change our different levels of our splitting. Though I will be honest, almost all of them, unless I tell you otherwise, are going to be octahedral, but you should always check. It's a good thing to know. So how can we check our coordination number for this chromium?
Multiply the charge by 2.
So if we did that, then our coordination number would be what?
4.
4. And if it was that, what shape should it be?
Tetrahedral.
Tetrahedral. So that's not how we find our coordination number. It's not always just multiplying the charge by 2. And that's because we have these neutral ligands in there. So a coordination number.
Atom surrounding.
So it's similar to the atom surrounding. It's how many ligands we have connecting once we take into account if they can connect more than once. So it's kind of like how many different atoms are connecting to that chromium. And so some of those ligands will just be 1, some of them will be 2, EDTA will be 6. So if we look at this water, how many times can water connect to that chromium?
4.
Right? There's 4 waters and each one does 1 connection. And for CN, how many connections does CN make?
2. Or 1. Oh yeah, 2.
CN only does 1.
Oh.
Right? EN, the biamine, does 2. A lot of times, if it's only 2, well, so cyano is special in that both the carbon and the nitrogen have lone pairs, so they can connect. But in general, you normally need about a length of 3 before they can really reach to each of the binding sites. it's a difficult challenge for both the nitrogen and the carbon to be orientated in a way where they're going to both be able to connect. So total, we have 6 binding sites. And so for your ligands, what you want to pay attention to are whether they're mono. Remember how to spell that second part of it. So whether they're mono, which means they make 1 connection, bi, where they make 2, or if they're EDTA, which makes 6. So now we know that we have an octahedral, and so we should have 3 lower energy and 2 higher energy states. So we get that's from octahedral from our coordination number. Because if we have to have 6 things surrounding it, then that's the only type of geometry that it can have. And so if we put in our 4d electrons, 1, 2, 3, is the 4th one going to go in the higher energy, or is it going to go in the lower energy? Is it going to go on the top, or is it going to go on the bottom?
The bottom.
The bottom. And how did you know it goes on the bottom?
Because it's a strong field. That's only.
Because it's a strong field. So strong field means that it's going to increase this distance between them to be a lot. So if you wanted to, you could imagine that a strong field makes it so that there's a big gap between them. Makes it a lot harder to get up there. So that means that our 4th electron is going to come down here at the bottom. And so how many unpaired electrons should there be?
Is it 2?
2. And so this is a good example of a question that might be on your exam, because it does require you to know a lot of those different parts in order to answer this, right? In order to get to the 2 unpaired electrons, you have to be able to figure out how many d electrons there are. You kind of need to be able to figure out your oxidation. Well, sorry, you have to figure out your oxidation state so you can figure out your number of d electrons. You have to figure out your coordination number so you can figure out whether they're split like this or if they're going to be split like a tetrahedral where you have your different orientations. And then from there, you have to understand whether a strong field or a weak field, again, how that impacts things for your high spin or your low spin. So this is one of those type of questions where it can fit a lot of things in there. And then maybe you would fill in multiple parts as you answered your question, right? Maybe you would fill in how many d electrons you had, how many, whether it's high spin or low spin, and you would go on and you would classify all of them. Does anyone have any questions on this? Our answer is down here. I guess I can put that in another color. Okay, then what I'm going to do is I'm going to split you guys back out into your rooms because I want you guys to actually discuss this where you have to support your claim. So we have cobalt and it's combined with A and it's combined with B, right? And so I tell you what color those solutions are. We have yellow and we have blue. And so what I want to get answered is which one has a larger crystal field splitting and then which ligand is stronger. And so I want you guys to talk about that with each other. So that way you guys can come up with some justification. And then when you come back, we're going to have someone from your group explain and support that. Does anyone have any questions? Okay.
appearing yellow, I'm guessing is a stronger lumen because it's able to absorb the stronger wavelength.
I agree.
Mhm. So it seems like you guys are all getting to the right place with it, right? And so when you think about it, when we talk about crystal field splitting, you're promoting an electron from the bottom level to your top, right? That's how you're going through with your photon. So as that light comes in, we're going to excite it up. And so the bigger this gap is, the more energy that photon needs. So the shorter the wavelength, then the more energy required. So as you guys talked about it, you were on the right track, that the color we see is the opposite of what's being absorbed. Right? So you can imagine this is red, orange, yellow, green, blue, violet. So if we are absorbing something that's yellow, or sorry, if we are being seen as something that's yellow, right? So we see this part here, then that means that we're absorbing something in this region. If we are blue, then we are absorbing something in the orange region. Right? So our complexes are going to be blue or yellow. And so right now that means that we should be looking for the one that is yellow in color, should be absorbing the shorter wavelength. Does that kind of make sense?
Yeah.
Yeah. So it's the opposite of what you would expect, right? Is the one that's looking like a longer wavelength is actually absorbing the shorter one. So the shorter the wavelength, the bigger the gap. And so then the stronger the ligand.
Okay.
So if you wanted to kind of go through and see it, it's kind of all written out here. But basically, the blue is the shorter wavelength, and so it has the higher energy. So our cobalt A6 must be the larger one. And that means that ligand A minus is a stronger ligand than B because it creates a larger gap. Okay. Any questions on that part? So we have just a couple more minutes. We'll try to wrap up a little bit of nuclear chemistry. So this one seems to be a challenging point for you guys, looking at some of your quiz responses. And so we want to think about where our material is and how it compares with our decays in order to get back to stability. So in this case here, oxygen 18, how many protons does oxygen have?
16.
Oxygen doesn't have 16.
8.
Got 8 protons. How many neutrons does it have?
This one has 10.
10. Okay. So oxygen 18, that's going to be way down here. We would have 8, we would have 10. And so we're kind of over here on the left-hand side of the island of stability.
I thought that if isotopes had both even numbers, then they were stable.
So it's not just that it's not just whether they're both even, because then you could have like 8 protons and you could have 30 neutrons and you would say that that's stable. It's that they are more likely to be stable. There's very few stable isotopes that are odd, right? And so that's about the magic numbers. So the magic numbers is just about how you find the most stable. It doesn't mean that you can't be stable and break those rules. It just means that our most stable ones cluster around that, and that has to deal with the binding energies. right?
Yeah.
And so that's a little bit above where we need to be worried, but it is like this idea that having even numbers and having specific even numbers in certain ratios gives us our best nucleus or our most stable nucleus. Right?
Yeah.
But the trends that we really want to think about is, does our number of protons to neutrons, does that ratio stay consistent for all of our elements? Is it always this 1-to-1 line, or does that change?
Changes.
It changes, right? But in the beginning, for our really small elements, it's about a 1-to-1 ratio. So would you consider oxygen to be a small element or a big element for its nuclei?
Well,
It's going to be small, right? So if it's telling us that we're not stable, right, because of this, if it was stable, then you could argue that like it wouldn't undergo any decay. But because I'm already telling you that it's going through a decay to arrive back at it, then that's how you can kind of make a choice. We're trying to get back to a ratio of a 1-to-1. Right? So we would like to have an equal number protons, equal number of neutrons. And this is true for pretty much any atomic number less than 20. Right? 20 is right here. And you can kind of see where our 1-to-1 line starts to really differentiate from that blue one. Right? So beta decay, what is that releasing?
Neutrons.
neutrons.
Right? So a beta decay, we're getting rid of an electron. So that means that we're taking a neutron, we're getting rid of an electron, and we're going to turn that into what?
Proton.
A proton. So we're going to remove neutrons and turn them into protons. So would that help our ratio of our 8-to-10?
Yeah.
Yeah, right? If we did that once, then we would become fluorine. We're 18, which is a 1-to-1 with each other. If we did electron capture, what does an electron capture do?
Wait, I thought beta decay, you're turning a neutron into a proton, so wouldn't it lose a number on the atomic mass?
So
Or it would
when
stay-
we look at this process here, does its mass number go down?
No.
No. So our mass number would still stay the same
Yeah,
because we have to keep that balance, right? So if we kind of imagine this as 18 oxygen and an 8, then this would become 18, 9, F, right? In order to keep all of that balance. So if we are doing electron capture, what does electron capture change?
The opposite of beta decay.
It's the opposite. So it's how we get rid of a proton and we turn it into a neutron. So would that help us achieve stability for this one?
No.
No. And so which one are we more likely to do?
Beta decay.
Beta decay, right? So beta decay is when we're kind of like in this region over here and we're trying to move back that way. We do beta decay. Electron capture is more on this side when we're trying to increase our number of our neutrons. So we're trying to shift it towards our left.
Professor,
Yep.
you said this is for atoms less than 20
Yep.
mass number of protons. Is that? But this applies to all elements, right? The
So
beta
beta
decay.
decay and electron decay applies to all elements. When you look at the 1-to-1 ratio, that's for atomic numbers less than 20. So that's only for these is the 1-to-1 ratio.
Okay, so you're just saying like when it's less than 20, the number of protons, it usually is like 1-to-1.
You're trying to get them 1-to-1. So if you look on your periodic table, the reason why all the way up to like calcium, they're so close to being an equal value between them is because most of the isotopes are going to be in that 1-to-1 ratio.
Okay.
When you get above 20, that's when you start to notice, oh, we have a significantly higher mass than doubling its atomic number. And that's because they have more neutrons now.
Mhm. Okay.
So alpha decay, that only happens up at the very top. right? And that happens because after atomic number 82, there's really no stable, or not stable, there's no non-radioactive isotopes, so they're working their way back down to that blue. And so that's when they go through alpha decay, is that they might be in the right ratio, but they're trying to move their way back down. All right. We have a question or time to do one more question. So I'm going to pull up one. I'm not going to worry about this nuclear reaction. I think that you guys are pretty comfortable with them. This one's different in that it's not just a decay. This one's actually a fission process. So you would want to practice that. We're going to do a rate one, kind of like as our last problem. And then there's an explanation part, but the answer is already there. So I think that you guys will be able to figure out that part. Right? So we'll just try to do this last one here as we work our way through. And so for this one, what we're talking about is we're talking about fresh rainwater has hydrogen or tritium, right? So it's a hydrogen water that's heavy, or hydrogen that's heavy inside of the water. And it normally produces about 5.5 decays per minute when we have 100 grams of it. Its half-life is 12.3 years. And so what we're going to do is we're going to check how old a bottle of wine is. Now, they're saying that it was produced in 1946. And so after we've capped it, are we going to be able to replenish this H3 inside of it?
No.
No. Right? Now that it's been corked, then our H3 is kind of like locked into place. So from there, it's only going to start to decay. And so what we want to know is if we're in 2020, how many decay events per minute should we observe? So we need to start with our there's two ways you can do this. One is you can do it all in one type of equation, or you can do your half-life first to solve for your K, and then plug that in to solve for your AT. But we know that the ln of AT, so that's how many decays we have at the end, divided by A naught, is equal to negative KT. We know that our half-life is equal to what?
ln2 over
ln2
K.
over K. And so if we imagine this, or if we want to, you can see this as AT over A naught is equal to E ln of 2 divided by our half-life times our time. So we can combine all those into one equation. Now, our half-life value, what should it be?
ln2 over 12.3. Or
so it should just be
12.3
12.3 for our half-life. Very good. What is going to be our amount of time?
74 years.
74 years. What should our A naught be?
100 grams.
Is the 100 grams what we're wanting to measure?
Oh, so A naught is what we're looking for.
So A naught is what we're starting with, but
Oh.
the grams isn't what we're concerned with, right? Because we have 100 grams of wine, we have 100 grams of water. That's not the part that changes. What does change though?
The decay event.
The decay values.
Oh.
So the 5.5. So you can imagine that this is like decays per minute. So the neat part about nuclear is that you can plug in different things. So you could do this in terms of concentration. You could do it in terms of nuclei, right? There's a lot of different things that you can put in there because we're just looking at their ratio. And so our AT is what we're looking for in this case. And so if we go through and we plug those in, we get something that looks like AT is equal to, or I have AT divided by 5.5 decays per minute is equal to e to negative ln of 2 divided by 12.3. And then the nice part is do we need to adjust our years, or are they in the same time scale?
Same time scale.
They're already in the same one, so we can leave those as they are. And so we get something like our AT. What value did you guys get for your new decays?
Like everyone's just waiting. Never mind.
Mhm.
Yeah, I think that there's something wrong with my calculator, but it's like I got like 0.0028.
So I have a little bit more than 0.0028.
Yeah, I think. Mm,
It does start with a 0 though, and a 0,
0.08.
0.8, and then I have this 4 or 50. And so that's what you guys are looking at for the aging ones. Do you guys have any questions about that, about how you plug those in?
but we could have just done like step by step, right? If we wanted to, instead of like
You
doing
could also have done it step by step, right? And found your K first and gone through that. That would also be okay. So for your exam, you've already seen several different types of dating problems, right? So there was the one on today where you guys had to find the final amounts. You also had to find half-lives, right? So all of that is tied up in with this, right? We also had it where we talked about you had like a certain fraction of the material left over, right? So you can, all that does is that just plugs in for the AT over A naught ratio. And so you just want to think about which number goes where. So if we've lost it, then our AT should always be smaller than our A naught, right? So just keep that in mind as you plug in your values. But there will be some type of dating question on your exam. So I would definitely recommend that. The last two questions, one of them is dealing with, this should be 10 to the 9. And this should be 10 to the 13. I'll have to fix those. One of them has you guys work through, like if we were an atomic bomb and we released 20,000 tons of TNT energy, and it just has you work through and figure out how much mass that would be. Then it also has you think about whether or not if we could collect all of those fragments of that bond and of that bomb and remass it, would it have more or less mass than before? And so there is a solution for this one already up on the next one, so you guys can kind of walk your way through that part. And so remember that whenever you deal with these nuclear processes and they're producing significant amount of energy, at the end of the day, we're probably going to plug into E equals mc squared. That at some point, when we want to think about the mass change or the mass defect, we're going to get that from the amount of energy released by plugging it into our E equals mc squared. And so remember that 1 joule is a kilogram meter squared second minus 2. So just get your mass into kilograms. And as long as you use the C from your chart, which is in meters per second, all of those things will work itself out. So the tricky part is just remember to get your mass into kilograms. The last question after that is just one where it's a little bit more like those essay type problems where you guys have to justify it. And so it talks a little bit about binding energy versus binding energy per nucleon. So the difference between binding energy and binding energy per nucleon is kind of a conceptual type of question. Because the larger your nucleus is when you form it, do you guys think you lose more mass or less mass compared to a smaller nucleus?
More mass.
More mass. So if we take 100 protons and 100 neutrons, that mass change is almost always larger than if we took 10 protons and 10 neutrons.
Yeah, I saw that it was always relative to the size of the element.
And so a lot of times what they do is they do it per nucleon to kind of account for that. Because that's how you can tell whether you're doing fusion or fission. Is fusion happens when you guys are on the low side and you're trying to work your way up and you're a small molecule. Fission happens on the larger ones where they're kind of a little bit less than their binding energy per nucleon, so they're going to release and break down in order to move themselves back up. And so in that chart, when you look at it, the binding energy kind of goes up really quickly in the beginning, and then it peaks out and then slowly drops off. Do you guys remember where this peak is?
It's like 200 and something.
It's not quite at, or sorry, not the value, but or what element does it kind of peak at?
83.
82?
82.
I forgot. 80.
It's iron. So it's in the 26.
Oh.
Yeah. So iron is where it peaks out at. It's actually one of the very interesting things about iron if you look into the process of the sun. The reason why there's so much iron, like our nucleus is full of, or the core of the earth is full of iron, and there's a significant amount of iron out there in terms of relative abundance, is because that's where fusion stops. So all of your stars kind of go up their way and they make a lot of the smaller processes, but they can't really get past iron. To make it hotter than that is when you have to have a supernova. And so all of those other ones, the bigger elements than that, past iron, they're going through like neutron capture or electron capture in order to increase past that point. But fusion kind of builds their way up to our iron, which is kind of like the apex. And then the other side, you can build a nucleus that is still got a lot of binding energy. It's just not quite as good as the iron. And so that's why there you go through fission as they work their way back up towards that iron. So iron is kind of like your peak. But I found a good question where I got this one from, and then I like their explanations. So I think that you guys should be okay with that part. But if you do have questions, we can definitely go over it. I have office hours this afternoon. I also have office hours on Thursday as well. I just don't want to keep you guys too much longer because I know I said that we were going to finish at noon and we're already past that.